In this video, we'll look at two more examples of finding areas of regions using polar coordinates. Now I want to find the area of one petal of the graph r equals sine of 5 theta. So the first task is to figure out what does this graph look like, and then what do I mean by one petal here. So let's start by looking at what this is just as a function of theta. So if I just look at normal axes, r versus theta, if r is sine 5 theta, what happens? Well, it means that I'm going to oscillate 5 times as fast, meaning that this first point here, which would be pi, is now pi over 5. Here's 2 pi over 5, 3 pi over 5, and so on. Which means if I'm tracing out different petals, when r comes back to 0, the petal ends, because that's where I've now pinched back off at the origin. So if we're to start to draw this graph, we can start at theta equals 0. And I know that for theta equals 0, I'm starting at radius 0. I'm going to leave the origin in a positive direction, and I come back at angle pi over 5. I'm going to leave this way, come up here, and come back at pi over 5. For the next loop, my radius is negative, which means instead of going in the radius positive direction towards angles between pi over 5 and 2 pi over 5, I want to go in the negative direction. So I'm going to have a loop that comes in this way, and then leaves through here. And that's going to be coming in at less than pi over 2 because 2 pi over 5 is still less than pi over 2. The next loop now has positive radius, negative radius, and then positive radius again, coming back into 0 at theta equals pi, because theta equals pi is now here, which is after 1, 2, 3, 4, 5 loops. Now if I keep going, I'm now starting at pi, but going in the negative direction. So I'm actually going to retrace this loop a second time, then this loop, then this loop, then this loop, and then this loop during 0 to 2 pi. So I'll actually trace this entire curve out twice between 0 and 2 pi. But the important thing here was figuring out the area of one petal. What that means I need to figure out when does my one petal end, and what can I do with that. So the first petal we saw ended when this came back into 0 or at pi over 5. That means my integral should go between 0 and pi over 5 to find this area. Let's set that up. We should have the integral from 0 to pi over 5 of 1/2 r squared. R is sine of 5 theta, d theta. I can use my half angle formula to rewrite this again. This becomes a 1/4 integral from 0 to pi over 5 of 1 minus cosine of 10 theta d theta. I can integrate that out. 1/4 theta minus sine of 10 theta over 10 from 0 to pi over 5. If I plug in either 0 or pi over 5 to sine of 10 theta, I get 0. The only thing that comes out of this is just pi over 5 times 1/4, which is a pi over 20. Another area that'd be hard to figure out in Cartesian, but works out pretty easily here in polar coordinates. We can also do things like area between two curves in polar coordinates as well. So we want to find the area inside the circle of r equals 4 cosine theta, and outside the circle r equals 2. So let's set up this picture. R equals 4 cosine theta is a circle of radius 2 centered at the point 2, 0. So that is this sort of a circle here. And r equals 2 is a circle of radius 2 centered at the origin. So it's going to look something like this. So the region I care about is inside the blue circle and outside the green one. So it's this region in here. And notice with how this is set up, the blue circle is the outside curve in terms of the origin being the focus point. It is further away from the origin always than the green curve. So I have an outside function and an inside function. I'm going to subtract the areas to figure this out. But to do that, I got to figure out where these curves intersect. So I need to first hunt for these two intersection points, and then I can go from there. So to do that, I just hit the two equations equal each other like you would normally in terms of x and y coordinates. Now it's just r and theta instead. So I'll set these two equal, and I'll get that I want 4 cosine theta equal to 2, which means I want cosine theta equal to 1/2, which this happens at theta equals plus or minus pi over 3, which that tells me the bounds on my integral. And how do I set up this integral? Well, for area between two curves, we can sort of combine things together because it was linear, but in this case, you want to make sure you keep separate the two inner and outer radii functions because you have to square them both first before you combine them. The area should be the integral from minus pi over 3 to pi over 3, 1/2 outer function squared, which is 4 cosine theta squared, minus 1/2 inner function squared, which is 2 squared, d theta, and then work this out and solve this. Integral from minus pi over 3 to pi over 3. 4 squared is 16, so I get 8 cosine squared theta minus 2 d theta. The cosine squared again becomes a 1 plus cosine of 2 theta over 2. And so that's going to be a 4 plus a 4 cosine 2 theta minus a 2 is going to give me an integral from minus pi over 3 to pi over 3 of 2 plus 4 cosine 2 theta d theta, which I can then integrate to get 2 theta plus 2 sine of 2 theta from minus pi over 3 to pi over 3, and then plugging this in, which gives me 4 pi over 3 plus 2 squared root for the answer. So that's another situation where you can apply this sort of polar coordinates approach to finding areas of regions, particularly if they are bounded outside and inside by nice polar functions. This approach also works well to find the area of these regions. Again, the point here is these regions could be really complicated to do if you didn't have polar coordinates, but now that you have them, it's another technique that you have to be able to find the areas of these regions when it applies to make it a lot simpler to do this as opposed to going by a brute force method by a different way. So polar coordinates can be super helpful in certain situations to help you find these areas of regions.